Hello, we will now introduce Mr. Matthew Moore, Global Subject Matter Expert for Condition Monitoring, Petrofac. He'll be sharing knowledge on advantages of risk-based condition monitoring. Mr. Matthew, over to you.
Good morning, Rai. Thank you very much for that kind introduction. Apologies, we've been having some technical problems, but hopefully you can see my screen now. Okay, thank you, Rai, for that warm introduction, and welcome to everybody that's joining us today. I'm Matthew Moore, and when I first started out in condition monitoring over 25 years ago, like many, I was somewhat thrown in at the deep end, inheriting the status quo without really knowing the strategy behind what I was doing. However, I soon found myself auditing and transitioning programs from other service providers, which typically meant there was significant room and certainly an expectation for improvement. As I gained experience, the lessons learned led me to adopt this approach, that many condition-based maintenance programs lose focus and do not meet their full potential due to inclusion of too many equipment items, poor data collection and analysis compliance, and ultimately a lack of prioritization of maintenance recommendations. Whereas adopting a risk-based approach provides focus on the most critical equipment, risk ranking and prioritization of maintenance recommendations, and optimization of resources. To gain these benefits, today we will discuss how to carry out a simple yet effective criticality assessment to optimize the equipment list to monitor, and then how to dynamically apply risk to prioritize maintenance recommendations. So where do we start? Well, by carrying out a criticality assessment, it will help us select and justify what equipment to include in our program. If we were to carry out a full failure modes effects and criticality analysis based on reliability centered maintenance principles, we'd first start out by identifying our systems and equipment. We define boundaries around this equipment and then identify the functions within those boundaries. We would then look at the failure modes that could stop that function performing. We would determine the consequence of each failure mode, then the likelihood that each failure mode would occur. The consequences and likelihoods are then combined to determine the criticality, and we would do this in the form of a risk matrix. For an entire plant with a few 100,000 tags, this process could take a team of people months. So is there a simpler approach? Well, if we look at a typical risk matrix, it's broken down into consequence of failure and likelihood of failure. Consequence of failure information is relatively easy to determine in ballpark figures for a particular plant. So for example, if we break our impact areas down into safety, environmental, production, and business, for example, in production, we can rank production from very low to very high based on limited loss in production to maybe an hour's loss in production to a few hours loss in production, going up to a day's loss or several days loss. Likewise, if we look at the business consequence, we can look at a repair cost that might be hundreds of dollars to a repair cost that's thousands, tens of thousands, hundreds of thousands, millions of dollars, etc. However, when we come to look at the likelihood data may not be so easy to come by, especially if it's a new plant. So not only is it difficult to come by, the information we may have might not typically be very accurate either. But for rotating equipment, we can simplify this process at a very early stage because we could actually ignore likelihood of failure for several reasons. Firstly, studies such as Nolan and Heap have shown us that most failures are random. So putting in an age relation to likelihood doesn't really make sense. And also, condition monitoring inherently is assessing our likelihood that something's going to fail all the time. That's why we're monitoring it. And also, we typically don't have accurate enough data that's actually going to add value in the first place. It can be easy, however, to tie yourself in knots allocating consequence of failure. So here I'm going to provide a few tips to make it easier. Break things down only into about 4 impact areas. I've seen people try and do 7 or 8 impact areas. It gets much more complicated if you do so. For example, in business, if we're looking at the total cost of repairing or replacing an equipment item, some people have broken that down into the cost of the item, a repair cost, a shipping cost, a logistics cost. If you bring it all together, it's much easier to put it into better ballpark figures. When you're looking at your ballpark figures, don't overlap the boundaries, because then it gets difficult to know which side of that boundary you need to be. One of the things I see as well is people try to make things overcomplicated, things that, oh, we need to use an algorithm to calculate this, or we need to sum all the impact areas, or we need to multiply them all together. I'm going to show you in a minute why this isn't necessarily the best thing to do. And actually keeping it simple is not only more effective, but if we only need to rank one area, it can save us a lot of time because we might not need to consider the other 3 areas. Also, people need to understand how to accommodate redundancy. For example, if you've got duty and standby equipment, it doesn't mean that you've lowered the risk in all of the impact areas. The place where it has most effect is on production. So if you've got a duty equipment and you can switch over to the standby, you are going to reduce how much production you lost because you can switch over. However, having more than one equipment item isn't going to make it any safer, and it's not going to make the cost of repair or replacement any cheaper. So let's say, for example, you've got a duty and a standby that individually would have a high consequence of failure. You can then, in the impact area of production, reduce it down to medium because you've got 2 items. So you'll have 2 items at medium rather than 1 at high. So to illustrate this with a few examples, looking at a main firewater pump for, say, an offshore oil and gas installation, this is a highly safety critical piece of equipment. It's going to rank very high for safety. It also has a secondary impact in that if you don't have any safety provision, you would need to shut down the plant and deman the platform. So a secondary effect would be production. Depending on who carries out this criticality assessment, they may not understand that there's a secondary impact, and they may only look at each individual impacts, in which case somebody in case A would come up with a different answer than somebody in case B. So if you use sum and product, the values will be different. However, if we're looking at its main impact, they would both come up with the same conclusion that yes, it's a very high consequence of failure. Also, if you've got something like a firewater jockey pump, this is going to be a small motor-driven pump with not much capital cost, no effect on production, no effect on the environment. However, it does have a safety consideration. If we use a maximum value, we are going to bring that into our program because it's going to have a high consequence of failure. However, if we used a product approach, because all the other values are low, we may exclude it, and that would have been a mistake. Also, if we look at things like small hydrocarbon pumps, they may be just a couple of kilowatts. They may not be that significant. They may not cause that much of a safety impact. However, I've seen some people skew their approach to make everything, for example, with a hydrocarbon or a corrosive fluid in it, as a very high safety. Well, that's fine if you're applying it to a large vessel, which would have a significant consequence if it failed, but a very small pump that could have a very minor leak and probably, that's a less likely failure mode, then it would rank lower. But what I've seen is all of anything that was hydrocarbon automatically went into a program when it wasn't actually that viable. And for example, under that same scenario, something like a very large seawater lift pump, which had a high business impact and cost to replace and repair, and it had a bigger impact on production, may have been left out at the same time. Another reason why not to use sum and product is if you are summing values out of 5, you're going to be a maximum of 20. But what does a value out of 20 mean? Does 5 out of 20 significant? Is 10 out of 20 significant? Do you need to be 15 out of 20 for it to act as being significant? And this is even worse if we multiply each of the values together to give the product, because now we're monitoring out of 625. So here we've got something that would rank it as a 40. 40 out of that value does not sound that significant. And 2 is obviously hugely insignificant. However, if we stick with our maximum value, It's very easy to explain to people why you've included it, because a 5 is very high and at the other end of our scale 1 is very low, and it's very easy to determine from that we've got a very low, and at a value of 3 we've got a medium, and at 1 we've got very low. So for many reasons I would always go with maximum value. It's the cleanest approach, it's the fastest to apply, and it's typically the most effective. So if we've determined what equipment we should consider for condition monitoring, the next stage is to find out if it is suitable for condition monitoring. So after the consequence of failure assessment, where we've gone through the master equipment list, we may have filtered down to our class codes. We've then looked at the consequence of failure of all the items and determined what's high and very high. If it's high and very high, we will then look at the failure modes which are detectable. And then we will look at the availability of monitoring parameters sensitive to the detection of these failure modes. Also, if we don't have a lot of equipment that comes out as high, very high, we might want to consider medium consequence of failure, in which case we may apply another criteria. For example, we may look at things over a 50 kilowatt power rating. And again, then when we consider them through this process. So once we've determined that we can monitor parameters sensitive to detecting failure modes, we will then look at the practicality of it. So if equipment is under duty and standby operation, we know we can run the duty, we know we can switch over to the standby, and we can test the standby. If the equipment is under intermittent but controllable operation, for example, like an emergency diesel generator, which gets run up, an hour a week or every month for test purposes, then we know we can monitor it if we plan to monitor it. However, equipment which is under intermittent and uncontrollable operation or short-term operation would not be practical for monitoring. Say you've got a knockout drum pump or a drain pump that switches on, 2 or 3 seconds intermittently every day or every week or every other week. You are not going to be able to plan to monitor it. And even if you used wireless sensors or something permanently mounted, it may not run long enough to collect the data. If we apply the same approach to our lube oil program, we've got a few slightly different considerations. Again, we'd go through the master equipment list and then the criticality, and we'd look at what's got a high or very high consequence of failure. We would then obviously ask ourselves, does it have oil lubrication? Then we want to consider what is the size of the oil charge, because if we're taking a sample on the machine, and by taking that sample, because it's only got a couple of litres reservoir, we have to top it up. It's not really practical for us to do lube oil analysis. One, because it's expensive and replacing the oil would be relatively cheap. And two, because the capacity of the oil is going to be on a smaller machine, for example, as well. So it's not going to be a significant machine. So once we've determined, yes, we're going to monitor it because it's a machine with a suitable size oil capacity, we're then going to ask, are sample points available downstream of mechanical components? If the answer to that is yes, we're going to ask, can we safely sample it while the machine's operating or just after it's shut down, so we get a representative sample of circulating oil? And if it's yes to both those cases, we can then carry out lube oil analysis to both assess the fitness for service of the oil and give an indication of the condition of mechanical components from where we've taken the sample. If, however, the sample isn't taken from downstream from any mechanical components, for example, it's taken from a lube oil reservoir, upstream pipe work, or downstream of a filter, we can still carry out oil analysis, but that's only really going to tell us that the oil is still fit for service. If the equipment isn't oil lubricated, typically it could be grease lubricated. Our majority of motors across the plant, we're not going to do grease analysis on. However, if we've got some very large bearings, such as slew ring bearings on cranes or turrets, for example, we then potentially consider them for a grease analysis. Okay, so now that we've determined what we're going to monitor, how do we apply risk dynamically to prioritize our maintenance recommendations? Well, people traditionally used a traffic light system, and that traffic light system would say red for action, amber for monitor, i.e. we've got an observation but we don't have a recommendation, and green would be satisfactory. However, this doesn't allow us to prioritize any maintenance actions. Everything that's red has got the same priority. If we used a risk-based approach, we can now use the same colors to represent low risk, medium risk, and high risk. Risk-based recommendations utilize both the consequence and likelihood of failure. We've already determined the consequence of failure when we carried out our basic criticality analysis. And now through our condition monitoring program, we can take live data from condition monitoring to identify the likelihood of a fault developing. And as that fault deteriorates, we can increase that likelihood as we go along. So how does consequence of failure influence our risk? Well, equipment with the same failure or the same fault will be higher ranked based on its consequence. So here we've got a machine that's got a consequence of 3 against a machine with a consequence of 4. As you can see, with the same fault, which is a high likelihood of failure fault at number 4, one gives a value of 12, one gives a value of 16. So we can automatically differentiate to the equipment that has the highest consequence and then obviously the highest risk. Whereas likelihood of failure is based on an analyst's, or in these days, it may be artificial intelligence and machine learning, the diagnosis of the severity of a fault. So when we raise a maintenance recommendation, we can give it a likelihood of failure. If we don't raise a recommendation, then by default, its likelihood of failure will remain at 0, so our risk remains at 0. If our subsequent analysis identifies something deteriorating, we can increase its likelihood as we go along, and hence the overall risk would increase. So to illustrate this in an example, we're looking at a developing fault on a rolling element bearing on a medium consequence of failure machine. So when we start out, if we're doing vibration monitoring, for example, we may see the first signs of an increase in our acceleration envelope levels. Our recommendation would be to grease the bearing. If, however, we start to see fault frequencies develop, as these fault frequencies deteriorate, we will be looking at medium risk, and that risk will increase with the stages of the failure mode we see or the deterioration we see, until we get to a point where we're going to recommend that it's more urgent to replace the bearing because we've seen multiple fault frequencies, something in our vibration velocity spectrum, and we're going to determine to replace the bearing, and now it's going to have pushed itself from low risk, medium risk to a high risk. The results of this means we can dynamically rank our machines. So if we've got a machine list and we've used this approach to dynamically apply faults to machines, multiplying the consequence of failure by the fault likelihood, we've now risk ranked that we've got some machines at high risk, some at medium risk, some at low risk. So we've got a basic traffic light system, but also with that, we've got a numerical value by which we can rank an order. And we also know the machine consequence of failure. So as well as looking at the machine status, we can also look at the actions individually. And we can see here with the list of actions, we've got actions associated with vibration, actions associated with lube oil. We've segregated them by technology, and each of the faults have their likelihood of failure. That likelihood of failure contributes to the overall risk of the machine. So again, we've got the machines risk ranked. A machine could have more than one fault, for example. When you close out the higher likelihood of failure fault, it will default back to the next likelihood of failure fault. And what I like to see when this is compiled together into what I call a risk assessment report or a machine evaluation is we want to know the risk status of that equipment item, that rotating equipment item. We want the details, the tag number, the name. We want to know its location and its operating context. And then we can use some images so people can visualize what the machine is. We'd know the compliance status. The compliance status is also important because if we don't survey a machine or we don't analyze a machine, we're not going to identify the faults with it. So we're going to have a risk status for each technology, and then we're going to have an assessment for each technology. We should support this assessment with some information. So for vibration, that might be a vibration spectrum, but for lube oil, that will be the laboratory report, for example. So in summary, the key benefits of a risk-based approach allow us to focus on critical equipment. They allow us to risk rank machines and also risk rank and prioritize maintenance recommendations. And overall, this will give us a greater confidence in business delivery. So I'd like to thank you very much for your attention, and I welcome any questions.
Thank you, Matthew, for the interesting and detailed presentation on this risk-based condition monitoring. There are no questions that I see. Okay. All right, and I shall end the stream. Thank you.
Okay, thank you very much.